In this video, I'm gonna solve a mixing problem where we have one tank. The flow rate, um, so going in the tank, it's 4 liters per minute with the concentration of 0.2 kilograms per liter. And going out, the flow rate is 3 liters per minute. I don't know the concentration, but I know the volume of the substance or the tank. It's 100 liters, and I also know that the mass of substance initially it's 0, or if you're thinking of a brine solution, let's say initially in the tank is pure water. So let's label with x of t the mass of salt or mass of substance at time t, and let's create the equation. So dx dt, the rate of change of mass of substance in the tank at time t, is the input rate, which is 4 liters per minute, times the concentration of 0.2 kilograms per liter, minus the output rate, which is 3 liters per minute, and then times the concentration, which I don't know. So I'm going to pause a bit and talk about the concentration, which is mass over volume. So in our case, the mass is x, and the volume is, well, it would have been 100 liters if going in would equal going out. But because the mass or the flow rate is different, we're going to say that the volume is 100 plus, because what goes in, it's more than what goes out, or let's think after 1 minute, we're going to have 101 liters inside, right? Because 104 minus 3 is 101. After 2 minutes, we're going to have 108 minus 6, so 102. So plus 1, or let's say 4 minus 3, so that we know from where it came, 4 minus 3 liter per minute times t, which is in minutes. So I hope it's going to make sense that we are going to end up just with x over 100 plus t. That would make it liters. So here would be the concentration. So times x over 100 plus t. And I can have the discussion in case, for example, we had a problem where we started with 4 liters per minute, but went out would leave 5 liters per minute. Then the difference would be that our concentration would be x over 100 minus t, because we would have after 1 minute 99 liters left. So that's just for discussion. So I'm going to erase this because that's a totally different problem. And now I'm going to solve the equation. So dx dt equals 0.8 minus 3x over 100 plus t. So this is a differential equation, and we learn in chapter 2 different types of equations. So I'm going to arrange this one a little bit, and I have an idea. I would write it as a 3 over 100 plus t x equals 0.8, which would be a linear differential equation. So I'm going to solve it. So here I did all the work. So it's a linear differential equation. T is the independent variable, x is the dependent variable, and here we figure out p of t, and then computed mu of t, which ended up being 100 plus t to the third. And the reason is we're going to multiply our equation by 100 plus t to the third. So what do we obtain? We get 100 plus t to the third dx dt plus 3 times 100 plus t to the second times x equals 0.8 times 100 plus t to the third. So the left hand side, it's actually d dt of 100 plus t to the third times x. And I always said, just look at the first term And it's exactly those terms that you see here, except the derivative. The derivative is coming in front, but always double check to make sure. Equals 0.8 times 100 plus t to the third, so we can integrate both sides with respect to t. The left hand side becomes 100 plus t to the third x, and the right hand side is 0.8 comes in front, and we get 100 plus t to the fourth over 4 plus c. We divide everything by 100 plus t to the third, and we get x of t, which is the amount of substance at time t, is 0.2 100 plus t plus c times over 100 plus t, so I'm going to put time to negative 3. We know that initially we had pure water or no substance, so this means 0.2 times 100 plus c over 100 to the third equals 0. And I did a little bit of computation to find c. So x of t equals 0.2 100 plus t minus 2 times 10 to the 7 100 plus t to negative 3. So this is the amount of substance at time t.